I start with a couple of questions from 6-2, I suspect, or even 6-1 is okay. Victoria? 6-1, number 23. Okay.
I can understand the concept of 6-1.
Uh-huh.
I'm just getting it all wrong.
Okay.
Every single one
Okay.
is wrong.
Okay. That would be really frustrating. Like, I understand. All right. So first thing we'll do is let's get a picture of what's going on, right? So I'm going to go ahead and I'm going to just use some software to do that. Is that okay?
Yeah.
All right. And I'm going to reset my graph paper to have trig marks on it. Oh, that's weird. Why did it do that? Oh, there we go. So we're going to graph y equals cosine x, which again, I suspect you know what that looks like from 0 to 2 pi, or 0 to pi over 2. But, and then y equals sine 2x, which again, should be able to do from 0 to pi over 2. So let's zoom in a little.
When I put 2 and then sine x, or I put
Sine
sine 2x?
2x. And then, we have x equals 0, and then x equals pi over 2. All right. So we're interested in this region here, right? So first thing we need to do is, we have two regions we're interested in, right? I'm sorry. And we have this region over here. So what do you notice is happening between the orange region to the red region?
There's a switch.
Yeah, they switch which function is on top, right? So over here we have sine 2x on top, but over here we have cosine x on top. Everybody can kind of see that? What we need to do, though, is we need to figure out where that switch is occurring. Okay? Now, ideally, we could do this algebraically by setting these two things equal to each other. If you weren't confident about that, how else could you find that point? You could graph them on your calculator and use the intersect command to get that x coordinate. It's going to be a kooky decimal. So I'm going to use my trig identity that sine 2x is 2 sine x cos x, which you may or may not be remembering. I'm going to move everything onto the same side. I'm going to factor a cosine x out. And then we're going to set those two pieces equal to 0 and solve them each separately. So cosine x is equal to 0 at pi over 2. Well, that's not surprising because that's the intersection right here that we can already see. And then here we have sine x is equal to 1/2. Which happens at 5 or 6. Good. So that is the one that I care about.
You only care about the 5 over 6.
because that's where they're switching. Right? I already can see that they're intersecting at
Oh, okay.
pi over 2. Like there was no surprise there based on the picture. All right. So we're going to have two integrals. We're going to have the integral from 0 to pi over 6. And then here it's going to be sine 2x minus cosine x dx. And then I have the integral from pi over 6 to pi over 2. And then they've swapped, so I have cosine x minus sine 2x. dx. Victoria, are you feeling okay so far? Okay. From here, standard problem, just doing integration just like we did last chapter. So this first integral, to do the integral of sine 2x, that's a u sub problem, right? So it'll become the integral of 0 to pi over 3 of sine u du, and I'll put the over 2 out front. But I'm not going to change the bounds for, oops, that's a minus, the cosine one, because I don't need a u substitution there, so I'm just going to distribute the integral as is. And then my next integral is going to be cosine x dx. Again, nothing to do there. And then my last one is going to be another 1/2 0 to pi over 3. Oops. 1/2, and then I have to do another u sub here, right? So u of pi over 6 is pi over 3, and then u of pi over 2 is pi. And that'll be sine u du again. So far, so good. And then now we're just doing antiderivatives from here. Elvis.
I'm sorry, what's the first interval?
Pi over 3.
Why is it happening?
Because I did the substitution with the u's. So I plugged pi over 6 in for u. So 2 times pi over 6 is pi over 3. That way, when I do my antiderivative, I don't have to like substitute the x back in. You could do it that way, and it's not wrong to do it that way. I'm just not going to do the extra layer of substitution. I'm going to change the bounds so I don't have to plug the x's back in. But you could do it. You could plug the x's back in and leave the bounds the same. That will give you the same answer. Sophia, or I'm sorry, Victoria, do you want me to keep going to finish this out? Or are you okay from here, you think? Okay. So the big trick was, or the big thing you had to observe was that the functions swapped who was on top there in the middle, and recognizing that you had to break that up into 2 separate integrals was the tricky piece. Is that what you missed? Yeah. Amanda.
Can you do 27 for 6.1?
Sure, that's right there also. Okay. So let's go ahead. I'm going to just generate a picture here real quick. Boom. Of course. So I have y equals 1 over x, and then I have y equals x, and then I have y equals 1/4 x, and I have x has to be greater than 0. Okay. Do one of those. Oops, that's not what I wanted. All right, let's put that down here. All right, Amanda. So that's the space that I want, right? So I'm going to need to know those spots, right? Okay. So I'm going to start by setting 1 over x equal to x.
I could find that. I'm just
Okay.
confused with how to integrate with 3 functions.
Oh, okay. So let's just do that real quick so that everybody can see what I did. And then we'll get to that part. And the setup's a little bit tricky here because, again, you got to set this up as 2 separate integrals. So obviously this is 1, 1 there then. And then I do the other one where 1 over x has to equal 1/4 x. So 1, let's do 4 is equal to x squared. So this would be the point 2, 1/2 then. So I'm going to set this up as 2 separate integrals. I'm going to go from 0 to 1. In that situation, my function on top is y equals x, and the function on bottom is 1/4 x. And then from 1 to 2, let's use a different color. The function on top is 1 over x, and the function on bottom is 1/4 x. Does that make sense?
Yeah.
Yeah, so it's just like you divide it into 2 separate regions because the function on top switched halfway through.
Okay. Thank you.
Yeah.
Like, how did you just choose like to make 1/4 x equal to 1 over x, or did you just make it equal to x?
Well, okay, so this line here is the y equals x line. And this line here is the y equals 1 over x line. So to solve for the intersection, I set those 2 things equal to each other, right? Similarly, if I want then this intersection down here, that's the 1/4 x line, and that's the 1 over x line. So to find that intersection, I set them equal to each other. I don't care where 1 over x and y equals x intersect each other because I know we're only worried about where x is greater than 0. So the lower bound I know already. And I don't care if they intersect anywhere else. I obviously see them intersecting at 0, but like whatever. Is that okay? Okay. And Amanda, you said you're good from there. Once we got the setup, you can finish her off. Okay. Right, and that's a good question, right? What happens when the function on top switches halfway through, where we have 3 of these things coming together? Well, it's not much different than if they switched who's on top and who's on bottom. You just break it up into pieces that, like, okay, just 2 at a time. That's all I can do is 2 at a time. which is what we did there. Okay. Should we do 6.3 here? No, Jillian says we got to. The good news is next class is going to be a day of like 6.2 and 6.3. We're just going to work on some problems together. Paul, what's up?
Do you know what we're doing during the next day?
Nope, not yet. Maybe we'll do the homework quiz or something in class on that day. Might be a good time to do that on the X day next week.
Did somebody steal your calculator cover?
Yeah. It's naked now. You know?
Is that on the board?
I don't know. Okay.
Maybe they didn't have a cover, so.
I think that they just, you're not supposed to have a calculator cover for the test. They were doing a test. I think they probably just put it in their bag and not thinking that it was, they were remembering that they borrowed it from me.
Yeah, what is their?
No, I mean, it's nothing. It's gonna be like a high five. I just have to put something up there to make them, to like go, oh, really? Let's find out what that is. It'll just be, it's worth your while. Whatever.
The reward is to see you smile.
Yeah, it's like, you made me happy, thank you. All right. So sometimes when we're doing one of these volume of revolutions problem, the disk method is not going to be easy to employ. So look at this example that we've drawn here, which is y equals 2x squared minus x cubed, and then y equals 0. So there's the blue region that we have. That's what we're going to be rotating about the y-axis. If I tried to build a washer, you know, my inner radius is here, and my outer radius would be there. The problem is, that's the same function. It's going to make it really difficult to come up with a way to write that cross-sectional area when for the same value of y, your function has two different x's that give you that value of y that you need to use as your inner radius and outer radius.
I don't see what you're talking about there.
So this thing is going to have, when I spin it around, it's going to have a washer cross-section, right? So the inner radius is f of x right there. The outer radius is f of x right there. It's the same function I have to use. So I can't just do f of x minus f of x. That's 0. Ugh. So like finding a way to rewrite this as an integral is going to be extremely challenging to try to do a washer here, because my inner radius and outer radius are the same function. Yuck. We're going to come up with a new method to kind of construct this volume that doesn't use washers or disks, that you'd want to use in this situation where you have the same function as like an inner radius and outer radius. Okay? So the idea here is we're going to build what are called shells. So think about like, you know, those Russian nesting dolls where you put like one in and then one over top of it and one over top of that, one over top of that. We're basically going to be building cylindrical shells. So it's going to be like an empty cylinder, and we're just going to be like fitting one inside of the other, inside of the other, inside of the other, or starting from the inside and stacking them outside. Doesn't really matter which way you want to think about it. Is everybody okay with that idea? We're going to then calculate the volume of each one of those shells, add up all those volumes, and that'll approximate the volume of our solid. So this is our basic shape for our shell. So the volume of that shell is going to be the volume of the outer cylinder minus the volume of the empty cylinder in the middle, right? So if the outer cylinder has radius R2 and the empty cylinder has radius R1, that's just going to be pi R2 squared H minus pi R1 squared H. And I could like factor an H out of that. I notice that R2 squared minus R1 squared is a difference of two squares. So I can factor that piece. I'm going to call R2 minus R1 delta R. And R2 plus R1 divided by 2 is like the average of those two radii. I'm going to just call that regular R. So what our formula breaks down to then is 2 pi r h delta R. What is 2 pi r? That's the circumference for the circle, for the base of that cylinder. H is like the height of that cylinder, and delta R is like the thickness of our cylinder, right? What are we going to do? We're going to make those cylinders infinitely thin, and then take infinitely many of those cylinders, right? Sophia.
What did you say the delta R?
The thickness of the shell. Okay, so let's relate this now back to a function, right? F of x, because this is like a geometric description. We're going to be having a function that we're rotating, so we need to kind of figure out like what is r and what is h going to look like. Hopefully, at this point, you realize that dr is just going to be like the dx, right? I think we've done that enough times now that you probably have a good intuition that that's what's going to happen there. So here is here's some function f of x that I've sketched in here in blue, right? And here's like the cylindrical shell that I'm building, one specific cylindrical shell. So the radius for that is going to be the distance from the axis that we're rotating our solid around to our sample point. In this drawing, that length is x. So the perimeter of that cylinder, or the circumference of that circle, that's the base of our cylinder, is going to be 2 pi x. The height of our cylinder is here, which is going to be the same, since we're starting at the x-axis, it's going to be the same as the y-coordinate for that point, which is f of x, right? So what we can say here then is that in this instance, we have 2 pi x times f of x times delta x. And that'll be that volume for our shell, right? Yes, Jack.
So I'm trying to visualize this. So the shell is you said it's like rushing this thing out where you're taking a section of it out of the cylinder.
So we're building the doll. So we're taking an empty cylinder, and that's going to be like the inner radius, and then we'll keep dropping them over to build out till you're all the way at the edge of the figure.
Oh, thank you.
And I have some pictures coming that'll make it a little bit easier to visualize what we're doing.
Okay.
Sophia?
So why is it a rectangle and not a
because we've just taken the cylinder, cut it, and spread it out. Because it's easier to calculate the volume, think about the volume that way than it is the cylinder, right? If I just like, oh, I'm just going to cut the empty cylinder, open it up, just a box, right? So let's go back here. Here's some function f of x that we're bounding between a and b in the x-axis. We're rotating that figure about the y-axis, so we end up with like, I don't know, it looks like like a squirt bottle cap or something, right? The cap on like a water bottle that has like an opening on it, kind of looks like that, like the Gatorade bottle or whatever. So when we build this out with shells, this is kind of what we're doing, Jack. So we have like an inner shell and then a next one and a next one, and they're just kind of stacking out. And if we make those shells infinitely thin, we end up with the same volume of the shape that we have. Does that picture, I think, shows a lot.
Yeah, I think we could. Thank you.
Yeah, and this one, I think it's harder to visually see what's going on because it's not as obvious of an approach. And that's the same way for me. I have a harder time seeing these ones than I do the other ones. Okay. So again, if we assume that these go infinitely thin, then our sum becomes this, which we know is the same as an integral, right? So there's our integration formula for the shell method. Okay. All right, let's do some examples now. So let's go back to that problem that we stated at the beginning, 2x squared minus x cubed, right? And let's now calculate the volume for this using this shell method we've just kind of talked through. So here, I'm going to be integrating. If we look here, we're going to be integrating with respect to x. It's kind of going to be the opposite rule as it was for the washers and discs, is that if we're rotating about the y-axis, we're going to be integrating with respect to x. If you rotate about a horizontal axis, you're going to want to integrate with respect to y. Okay. So if I look here, the radius of my cylinder is x. The height of my cylinder is like the y coordinate here, which is f of x, or 2x squared minus x cubed. And the radii for my cylinders should go from 0 to 2.
What about the delta R?
The delta r is the dx,
Oh, okay.
right? Okay, so how do we do this integral? I wouldn't do u sub on this.
So, take that constant, put it from integral, and then distribute.
Yeah, that's the verb you guys are searching for. I heard lots of D words that weren't distribute, but that was the one I was looking for. Everybody's okay there? Okay. So we'll do our antiderivatives. Notice that that first antiderivative we could reduce. So I have 2 to the 4th is 16 divided by 2 is 8 minus 2 to the 5th is 32 over 5, and then we have the minus 0. 8 is 40 over 5, so that's going to be 8 over 5 times 2 pi, so 16 pi over 5. So this one felt pretty easy, the setup, right? Takes a little bit to kind of visualize what's going on, but once you've got it, the hang of it, the setups are easy, although it's hard often to visualize what's going on. Elvis, what's up?
So we're rotating the little bump across the y-axis.
Yes.
So how do we get that rotating?
So that's not the shape of the three-dimensional figure. The shape of the three-dimensional figure is going to be like something that goes like down like that, and then has like kind of bulged, like kind of like a bowl with a funnel built into it or something. But what we're doing is we're like building like a cylinder around this thing. So we have like one little tiny cylinder here, and then like another cylinder here, and we're just kind of building up. Is kind of what we're doing to approximate the volume. So we're just kind of following that inner ring and building a cylinder, and we're just going to keep stacking them out and out over top of one another until we've covered like the entire volume. Does that?
Yeah, that makes sense.
Okay. And again, I apologize with my like terrible three-dimensional drawings. These are really difficult things to draw in 3 dimensions, and then to like draw another three-dimensional figure inside of that that's like filling the volume. Like, oh my goodness. I need like a degree in fine art to do this. Or some really nice computer software that I don't have either. Okay. Let's look at another one. So here we're going to be using cylindrical shells to find the volume of the solid obtained by rotating the x-axis of the region under the curve y equals square root of x from 0 to 1. So this time we're rotating about the x-axis. What kind of shape is this going to be forming? Kind of like a hemisphere, right? Except it's like on its side, right? Where we have the flat side here, and then its bump is to the left or whatever. You guys kind of see that?
Why wouldn't we be able to use?
You could.
Oh.
You could. Right now, we're practicing just identifying the parts for the method. But yes, you could absolutely do this by discs, and it would not be difficult either. So you're going to find that there's stuff that you could use on either one. It's not a big deal. Stuff that discs or washers will work decidedly better on, and stuff that shells will work decidedly better on. And the next class is going to be, I'm going to give you a bunch of these problems, and you're going to have to decide which method to use. Okay? Because we have like kind of 3 methods, disc washers and shells. When do I decide when to use which one? Because if you picked wrong, it can become a very difficult problem, which is usually a good sign of like, no, try something else. But yes, you could absolutely do this with shells. All right. So first thing you should notice is because we're rotating about the x-axis, I'm going to be doing this as a dy integral. Everybody's cool with that? Okay. So if I'm rotating about the y-axis, the radius for my cylinder is going to be that distance. Everybody's okay with that? Since that's the pivot point for my rotation. That distance is the y coordinate for that point. Is everybody good with that? That y coordinate should be I know that x is y squared, so this should be like y squared comma y, right? That point. Is everybody okay with that? So that distance is y, so we have 2 pi y. Everybody's okay with that? So then this is going to be like the height of my cylinder. Everybody's okay with that? So from here to here is 1, right? So we're going from 0 to 1. Here to here is x, right? Because we're going x over. So my height should be 1 minus x, or 1 minus y squared. Because at that point, the x coordinate is y squared.
So we're given that the x coordinate is y squared. That is what that means.
We figured it out. Because y is equal to x, square root x, so x is equal to y squared.
Okay.
Because I just squared both sides of that equation, right?
So
So Sophia, why did I know to do that? We're integrating with respect to y. Everything I write down in here needs to be in terms of y's, not x's.
So the x equals y squared on your y-axis. That's
Mhm.
not something that's normally given in the problem.
Correct. Correct. I figured that out from the function that was given, and then I wrote it in after the fact. What are my bounds of integration going to be? Yeah, so we're looking at the y going from 0 to 1. Is this okay? I'm trying to go slow and walk through this steadily and really explain how I'm getting things. Did we miss anything as we're doing this? Do you want to erase everything and walk through it once more? Yeah, of course. We can absolutely do that. I'm not going to erase the integral, but I'm going to erase all these marks and explain where I got the things. Okay? So this tells me dy. Looking at the y-axis, 1 to 1 tells me the bounds of my integral. So far, so good. The radius for my shell is going to go from the axis of rotation to my function. That's my radius for my cylinder. That cylinder that's the point x comma y, so the radius is y. The height of my cylinder is going to be back over the shaded piece. Yeah, Elvis?
I mean, choose to go straight down the middle, from the axis.
Well, I'm just picking like an arbitrary one. It's not. This would not be the first one that I would build, but I'm just building like an arbitrary cylinder because all I need to figure out is symbolically what is R and f of x, or R and h, so that I can plug them in. So it doesn't. There's nothing magic about the spot I picked. wouldn't start there. We're starting at 0, but I can't draw something that small and label it. It would just turn into like a bunch of mush. So I just pick something through the middle where it's easy to kind of label. Is that okay? Jillian, you had a hand?
No.
Okay. So this is like the height of my cylinder. So I know that this distance is 1. I know this distance is x, because that's how we plot a point, right? So the height is 1 minus x. The problem is that we can't have an x if we're integrating with respect to y. So I need to convert x in terms of y. So if I know y is equal to the square root of x, I square both sides, and I have x is equal to y squared. So that's the height that I plugged into my formula. Now we integrate. So just like before, I'm going to distribute and pull the constants out, do my antiderivatives. So I have 1/2 minus 1/4 is 1/4. I guess I should have written the yeah. So 1/2 minus 1/4 minus 0 is 1/4 times 2 pi will give me pi over 2. Victoria?
I just have a question about finding the y-intercept. So we know that x is equal to y squared, but like how do we know that the y-intercept is just y?
The y-intercept?
What's the y? Like it's a y squared y.
Oh,
Like how
that
do we-
point?
Yeah, how do we know it's just y?
Because we're just treating y as the independent variable. We've just rearranged it. Like normally you write it, it's like x comma f of x.
Okay,
Here we've written it as y comma f of y.
okay, and it's just y.
And the reason we want to do that is because we're integrating with respect to y. That's like our independent variable.
Okay.
Does
So
that-
y just doesn't change.
Correct.
Okay.
Yes. Just like when x doesn't change, we write it as x comma f of x or whatever. If this was rotating about the other axis, we'd write this as x comma square root x, right? Instead of x comma y. Does that feel okay?
Yeah.
All right. All right. Next one. No picture this time. We're going to have to supply our own. Okay. All right. Should be able to do this relatively easy. What does y equals x minus x squared look like? So what? So it's a parabola. Which way does it open?
No, down.
Down, because the x squared is negative. What are the x-intercepts? 0 and 1. Everybody's good with that? You could set the thing equal to 0 and solve. You'd factor off an x, set each term equal to 0, x equals 0, x minus 1 equals 0. So I'll go ahead and make a picture and drop it in now. Again, probably would not have to do that without a calculator, but I like on ones like this that it's no reason you could not do that in your head, to talk about how you could do that in our head. And then y equals 0. Okay. Give me some zoom ins. That's too many probably. Oh boy, that got real big. Okay. And then we're rotating about the line x equals 2. Okay. First things first, are we integrating with respect to x or y?
It's why.
It's the opposite rule as the disks. It's x.
Wait, how did you know there was hard in that way?
Well, it says
Line X equals
it's rotate about the line x equals 2. So it doesn't matter which way you do your circle, right? Like it's
Oh my gosh, that is sorry. Sorry, sometimes I just.
okay. What are my bounds of integration going to be?
0 to 1.
Just 0 to 1 because that's the only space that's going to exist, right?
So would this problem actually be the same if it said about the line x equals 1?
No.
But okay. Oh, because the negative portion, No.
This much of it would be the same, but what's going to come after this will be different. Because one of what comes after is got a hole in it,
Right, yeah.
and the other one doesn't. And because the hole is a bit wider, there's more stuff, right? Like if you make a donut that's like this with a hole this big and a donut with a hole that's this big, those have two different volumes.
Wait, where is the portion that is the... Oh, I understand.
You good?
Yes.
Okay. Sometimes you just have to
They're so hard to learn.
It is. Yep. It takes some practice for sure.
So, would the shape kind of be like, use like a hill on a circle, and there's going to be a hole in the middle of that?
It's like a bagel, because you have to cut it in half.
Yeah, it's got a it's a like a funnel shaped pipe,
One half.
Okay.
but it's not like smooth on the outside. It's like a hill with a funnel in it. Yeah. Right, like the bottom is flat. It's got a bulge on it, but there's like a hole through the middle.
Oh, so the bottom's flat?
Yeah.
Okay. Alright.
Yeah, because the bottom, this side is flat, right? So when you spin that along, that edge is still going to be flat. And there's going to be like a hill on top and a hole in the middle. Yeah. All right. So we're going to pick some arbitrary point here. So that's going to be my radius, right? To some arbitrary point between 0 and 1. And the distance from the axis of rotation to that arbitrary point would be the radius of some cylinder. Not necessarily the first one or even the last one, just some arbitrary cylinder. So what is that r going to be? It'll be 2 minus x.
Oh, I like that. Mr. Cool.
Because we know that this distance is 2, and we know this distance is x.
How do you know that?
Because that's how you plot a point. You go x to the right, and that's our point. No? Victoria, was that not a good enough explanation? You made a face like that didn't help me at all.
But why is just that? Would it be a half?
Well, if that value there is x, that point,
It is? Why?
I just picked it. I just picked an x value between 0 and 2, or 0 and 1, and I'm calling it x.
So now I understand why. It would be like 2 minus. Okay.
Okay?
Mr. Cool, I'll run with that. That's
Yeah, homie. So that is going to be like, that's going to be like the height then, right? If that point on the x-axis is x, this is the point x comma y, so the height is the y. In this case, what is the y on that curve?
X minus x squared.
And we're set. Integral time. So what are we going to do there? Yep, and then foil it out. X cubed. So the hard part is the set, right? Getting the setup set, finding the values for R and H. Once you've got that, though, it's okay. Jack.
So can I just ask?
Yeah, big
a question
picture.
about the setup.
Sure.
So when you did that R, the radius equals 2 minus x. For every other problem we've done, it was just the variable. We did it 2 minus x because it extended past the original function, whereas in the others,
Well, if you look at the other one,
it was just the height of the function.
we're going from the axis, went through the shaded part,
Yep.
so nothing changed.
Okay.
Here,
This one did go-
the radius went outside of the shaded
Yeah,
part.
that's what I was trying to
Yes.
say.
Yes. And notice here the height went through the shaded part.
So
Nothing changes.
Okay.
But here my height had to go back, like the wrong direction.
Yeah.
That's why you end up with the minus. Yeah.
Okay. Okay. Okay.
Yeah. Good idea looking for those like geometric patterns of like when do I have to adjust these things and when is it just the thing.
That makes sense.
Sophia, you're next, Taylor.
How do you know that H is 1? Is that just like a given? Like you just
Okay. So it was because this is going to be like the height of my cylinder, right?
is at the point. At
Like I'm building, like a cylinder like that.
Right.
So the height is the y coordinate for that x,
Right, because that's the height.
because that's as high as the function goes.
Okay.
Does that?
Yeah.
Okay. Taylor.
So just to clarify, like the steps for it.
Mm-hmm.
So like you graph it out and you like draw it and visualize it. And you like find each component for the formula.
I would find R first and then look for H.
Okay. And then you like take the antiderivative.
You plug them into your integral formula and then do the antiderivative.
And then just solve
Yep.
some graphs.
Yep.
That's just the function.
All right. So your guys' assignment for 6.3 is that first part. Part 2, we're going to do this in class next time. So this is the one where you're just going to be like given a problem that could be done with shells, washers, discs, and you're going to have to like figure out the method. No, we're just going to work on it together in class because like we need a day to like process this and like do some guided practice because this is not an easy skill. What do we got here time-wise?
We have
Do you want to do a couple of from the homework here to start? I'm cool with doing that.
I hope we started.
Yeah, for sure.
I think that's a great idea.
All right. So first things first, going to generate a picture. Bloop. And again, you could do this on your graphing calculator. It'll be just fine. Okay. Oh, I forgot the x equals 1 in there. It's because I wrote y equals 1. Dum dum. Okay, that picture is wrong. Sorry. Okay. So this is the region, and we're rotating. In the question it says about the y-axis. So we're going to be integrating with respect to x. What values? What are the bounds of my integration going to be?
0.
Everybody feels okay there. Okay.
Wait, how do you know if you're integrating x or with respect to x or y? Again?
It's the opposite of whatever you're rotating about. So if you're rotating about a vertical axis, use the x. If you're rotating about a horizontal axis, use a y. Is the typical. I don't know if that's 100% every time, but I did all the homeworks and I think that rule worked for me every time. So I think it's a pretty good one.
Wait, how did you know it was 0 to 1?
I mean,
Oh my God.
I just looked.
Okay.
I looked at the x's that covered the shaded region. This is 3 that we're doing right now. The first one. Okay. So I'm going to pick like an arbitrary value between 0 and 1. I'll call that x. That's going to correspond to the point here, which is x comma y. Everybody's okay there? So which is the radius, the vertical part or the horizontal part? The radius goes from the axis of rotation. So that's the horizontal is the radius, and the vertical piece is my height. So 2 pi x, comma, and then the h is just cube root x. Done, right? Just integrate from here. Everybody's okay with that? I'm just going to do setups. I'm not going to, in the interest of like doing some more exampling with you guys, we're just going to do setups. I'm not going to actually compute anything. Is that okay?
So like h is y, you know that y is cube root of x.
Exactly.
And then the radius is just x because you said it was x. Right?
Yeah.
And then you made that line like right there, but you could have made it anywhere.
I could have picked the x to be anywhere, right? It's not going to change fundamentally. It just names a thing so I can visualize what's going on. What do you guys think? 5 next?
5 looks.
Or do you want to do a different section?
We do 5. That one looks gross.
Sure.
to the negative squared.
Well, I have stuff.
Wait, do we have a physics test next week?
Yeah.
It's on Sunday. See, we got a physics test on Sunday. What?
Those are things you can tell Sergio. You shouldn't tell anybody else things like that, though.
Sergio, we have a physics test.
I'll let you pull up.
Sergio, what's
Wait, what are we talking
about?
Yeah, I was.
All right. So here's 5. Again, rotating about the y-axis, so we know we're integrating with respect to x. The bounds of my integration should be,
0 to 1.
I guess I should have drawn in the, there.
Wait. Oh, that's the one. Oh, it's 1 minus. Radius is equal.
So far, so good?
Are we rotating with x equals 0?
That's the same as the y-axis, right? These problems all said rotating about the y-axis.
Yeah, well, like x equals to
Yeah, x equals 0 and x equals 1. So yes, this is also the axis of rotation in this problem. Yep. Everybody's so far so good? Okay, we'll pick an arbitrary x. So that's the point x comma y. What is the horizontal component? That's the radius. The vertical component is the? So just 2 pi x and then e to the negative x squared. What are you going to have to use to integrate this? Got to be a u sub problem.
Where did e negative x squared?
That's the value for y. That's the function.
Oh, that's the given.
Yeah, this was just like x comma e to the negative x squared.
I have a question.
Yes.
If it was over the x,
Uh-huh.
like y, would the radius not be horizontal? It would be vertical.
So this would be the radius,
Okay.
and this would be the height. No, sorry, this is still the height. Excuse me.
So. Wait, that's the wrong problem.
Does that feel okay? Okay, I'm going to erase all those hypotheticals there. Probably have time for another. Do you want to do another one? The other ones are now to the x-axis. Do you want to do one of those?
I try.
I'm not saying much of it. Yeah.
It takes like 2.5 hours.
No, because I get it. Once you conceptualize it.
Oh, let's use it.
That's like anything.
Here's a quick aside. What does xy equals 1 look like? X times y equals 1. What does that look like?
1 over x.
That's the same as y equals 1 over x. Yep, so that's like a hyperbola. Just FYI, as you're going back to look at these, I've tried to color code them. So like whatever I circled the number in is the same color I did to do the work for the problem. So like I did red, then blue, then green. If we do another one, it'll be like orange or red or some other, some other unused color. All right. And we're doing this rotating about the x-axis now. So what does that tell me? dy. The bounds are going to be yes. Since we're integrating with respect to y, the y-axis is where we look for our bounds. Okay, so I'm going to pick like an arbitrary y this time. I'll put it down here. It gives me a little bit more space. So there's my arbitrary y. So there's my x comma y. Okay. So which one is the radius, the vertical or the horizontal? Vertical. Great. And the height then is the horizontal. Okay. Okay. All right. So what, yes, go ahead.
Well, why is the radius like all the way down there if it's only from 1 to 3?
It's only from 1 to 3. Because the axis of rotation is the x-axis. So like if this is the x-axis and we're building our cylinder, the radius of that cylinder is going to be from the x-axis up to the function.
Okay, would it go all the way up to 3?
Well, even if, like, here's the thing, like, it depends on where you're picking this, right? Like, it's getting bigger. The hole is getting bigger as you go closer to the closer to the y-axis.
Oh, yeah, okay, yeah.
You get what I'm saying? Yeah. All right. So, what is the height then? So this is y, h is x, right? But what is x going to equal? 1 over y. So we have 2 pi y times 1 over y. And that should be easy integral to do because the y times 1 over y just cancel each other out. So just integrating a constant. Okay. So it'll be 2 pi y from 1 to, evaluated at 1 to 3. So it'd be like 6 pi minus 2 pi, so 4 pi should be your answer.
But why is it 1?
Huh?
Isn't it 1?
Yeah, I did the antiderivative of 1 is y. That's okay. Yes, you're 100%. I was just like a step ahead. What's up?
Why is your
Because it's the, so if this is my point, how did I get to that point? I go x over, right? And then y up. So it's that horizontal distance is x. You want to do one more? We probably have time to do one more if you'd like. Do we have time to do one more?
Are there problems with application? Like, are there gonna be word problems with these? Like, what's an application of 3D?
Well, so this would be like you're actually designing a product.
Oh.
You're probably doing that in like a CAD.
Oh, what quantity of material?
Yeah, like
That's kinda cool.
you're defining, okay, the exterior of this product is defined by this curve, and then we're rotating it about this. Like, how much material do we need for this?
That's good.
You know, like that's the kind of like an engineering, like a manufacturing perspective that you can see this becoming like, oh yeah, if you're cutting product to look like this, even if you're doing like a 3D print of something, which is very much like what you're ending up building is like something that could be 3D printed.
That's cool, that makes sense.
So,
All this math, though, could just be like done in CAD.
yes, and in practical terms, it would be.
But it's cool to know how to do.
But so could most of the stuff you do on your calculator. Could just be done on the calculator. Why do I need to know how to do it by hand?
Yeah.
I mean, it's like at that point, it's like, well, what happens if I smash your calculator? If I take a hammer and be like, do it now.
You're just like in your office as an engineer and someone smashed it. And you're like, I won't.
But like, how are you supposed to go any further if you don't understand how it works,
Yeah, no.
right? Like that's the idea. Alexis.
But to me, the like stacking cylinders with I know if you're taking like infinitely many, is there one that's more accurate though? Does it depend on
The question is going to be which one of the integrals is going to end up being easier is the question you want to ask.
I'm just wondering.
Because no, they'll both give you the exact same answer. The problem is, depending on the situation, the integral might be almost like kind of impossible to do by hand. Like you'd have to do like a numeric approximation for it. Or like the setup might be like next level difficult.
Oh, but it will give you the same answer.
Yes, they will give you the same answers. It's going to be, the question is going to be like, is this amount of setup needed going to be the same? Or the amount of solving power needed the same? And more often than not, one of them is going to be significantly easier than the other. And that's what we're going to look at next time when we work through those, the part 2 for the homeworks, 37 to 45. That'll all be something we explore together. So for Sunday, sections 1 and 2 is the problem set that's due. So we'll worry about 6.3 will go in next week. So we'll take a day next week and do this second part of 6.3 homework. We'll do 6.4. We'll probably do the homework quiz on that X day. And we'll wrap up section or chapter 6 after we get back from break. How's that sound?
Sounds good.
Okay.